Hello everyone and welcome back. Hopefully everyone got a chance to try and think of a solution themselves. If you haven't, that's perfectly fine. This is a pretty challenging problem. What I'm going to do is I'm actually going to highlight some of the similarities to how this question ties to our previous question of the water container. But I'm also going to highlight some of the new abstract thinking that we need to have in order to understand the differences and how those differences can help lead us to coming up with a solution. So one of the first things that we notice is that this question, unlike the previous question, requires us to actually use the entire array in order to generate the solution. In our previous question, we were only required to find any two elements in the array that would add up to some greatest container of area of water. Whereas in this question, it's almost as if we're trying to figure out how much area of water could in total be held in the entire array itself. And this is much more clear with this visualization. But this question does share some logical similarities to our previous question about finding the maximum container of water. In fact, if we were to just focus on this section here, this little container of water formed by the 1, 0, and 2. If we look here, we'll notice that there's some similar logic in the sense that the smaller height of the two walls that form this container is the actual one that determines how much water can be held. Or at the very least, what's the maximum amount of water that can be held? Because we know that the height of water here can never exceed the height of the smaller of the two walls, particularly this one. So keeping this in mind, let's see if we can take that logic and see if there's any differences with a different body of water. Let's look at this 2103 area here. Here we see that it's the same in the sense that between the 2 and the 3, which form the container of our body of water, the 2 is the one that actually determines the maximum height that the water can go up to. Now, the next thing that we do have to realize, though, is that inside of this body of water, this section right here, the 1, cuts into how much body of water we have. This then tells us that not only is the smaller of the two walls that form the container determine the height of the water, but also that the heights on the inside of the container also affect how much water is inside. This becomes really apparent if we move over and look at this container here, the 31012. We know that between the 3 and the 2 is the smaller side, so the maximum amount of water that can be contained can only be of height 2. But what we also know is that the 2 ones inside between the two walls also reduce the amount of water that can be captured within this container. So this kind of changes how we would approach this if we were to follow our original question of container of water that we just did. Because in that one, as long as we had the two sides, yes, the smaller side was the one that affected the area, and yes, the width also mattered, but we didn't have to account for this additional blockage here. So here we're seeing that we're actually breaking up this problem into much smaller problems. Instead of focusing on the array as a whole, we're trying to focus on smaller sections so that the logic is easier for us to figure out. In fact, we can even go a step further. Then what we want to do now is actually focus on individual elements, and based on those individual elements, try and figure out if we can determine how much water can be stored at any given element. Meaning that if we were to look at this element right here, this 0, what we notice is that the container is formed by not the immediate walls to the side of our value of 0. It's not the 1 and the 1. In fact, if you remove this 1 and 1, just imagine that these were both 0. This container would still be formed because some value to the left and some value to the right of our current value of 0 is higher than our current value. The 3 and the 2 are both higher than 0, meaning that a container can be formed. But let's sub these ones back in. So imagine it's exactly what we see here. We don't form the container for just this value of 0 with just the first values that are higher than 0. This can be very easily demonstrated with a different diagram, which I'm going to draw for you. So let's look at this graph that I've just drawn for you here. And what I want you to focus on is this 0 value with the P under it. If I were to ask you how much water is above this value, what you would probably do is you would rationally think, okay, what's the container size? Well, here, the container we can visually see is formed using the 4 and the 5. And the logic here is that the 4 is the greatest value to the right of our P, and the 5 is the greatest value to the left of our P. There are values in between, but they don't form the actual walls of our final container. It's going to be the greatest values, the max values left and the max values right. With the 4 and the 5 then, being the walls of our container, we take the smaller of the two sides, which is this 4, and then we subtract it from our current height of 0. So 4 minus 0 gives us 4. And that's how much water is above this P. And just like that, we realize we've actually just come up with the formula for calculating how much water is above any single point in this array. And we can actually test this using another pointer. Let's just point at the 3 instead. So looking at this 3, we do the exact same thing because our container hasn't changed. We go all the way to the right and we take the maximum value, which is the 4. And then we go all the way to the left and we take the maximum value, which is 5. We take the lesser of these two, which is 4, and we subtract it from 3 to get 1, which we know is that there is 1 block of water above this 3. So here we've pretty much proven that this is going to be what we need to do in order to calculate the area of any element in the array. And how we can say this as a mathematical formula, or at least some kind of formula that we can use to keep track of, is that the current water for the current area that we're in is going to be equal to the minimum between the max left and the max right, subtracting our current height. So that's what CH is. CH stands for current height. And just like that, we now have a general formula to calculate the water at any element in the array. So if we wanted the amount of water for the total number of elements in the array, then we just apply this formula to every single element, get the water, and add it to some total that we keep track of. By the end, when we've applied the formula to everything, then our total will be the final answer, which is going to be the total water inside of this array. So let's try it with our original diagram, which is this array. Just ignore this diagram for now. What we'll need to do is we'll need to keep track of some values. We'll also need a new pointer here. So let's initialize it on the left side. And what we'll need is a total water. So I'm just going to call it total. We also know that at any given point, we need to make sure that we have the maximum left value and the maximum right value as we discussed. So let's get a max L and a max R. What we'll do then is initialize the total at 0, and the max left and the max right will also be initialized at 0. So what we need to do here is we need to start at P and we need to say, okay, are there any values to the left? No, there aren't, so max left stays at 0. What are the values to the right? Well, first we have a 1. 1 is greater than 0, so then we would switch this for 1. Then we move right again. 0 is less than 1, so then 1 stays. 2 is greater than 1, so 2 becomes the new max. Then we move right. 1 is less than 2, so we keep the 2. 0 is less than 2, so we keep the 2. 3 is greater than 2, so then we replace the 2. And then we move right. 1 is less than 3, we keep the 3. 0 is less than 3, we keep the 3. 1 is less than 3, 2 is less than 3, so we keep the 3 as our max R. We take the minimum according to our current water formula between the left and the right value, so 0, and then we subtract it from our current height, which is 0. 0 minus 0 gives us 0. Adding it to the total, total doesn't change, it stays at 0. Our P then moves forward, and we have to reinitialize our max R. So here, P moves forward, max R is 0, and we do that calculation again. We go left. Is 0 greater than 0? It's not, doesn't matter anyways. 0 is our max left. Then we go right. 0 is not greater than 0, so it doesn't matter. 2, though, is greater than 0, so we replace this 0 with a 2. 1 is not less than 2, so we keep the 2. 0 is not less than 2, we keep the 2. 3 is greater than 2, so we now increase this to 3. 1 is not greater than 3, so we keep the 3. 0's less than 3, we keep the 3. 1 is less than 3, 2 is less than 3. We do this calculation again. What's the minimum between our left and our right? Our minimum is 0. 0 minus our current p, though, is 1. 0 minus 1 actually gives us -1. But we don't want to add that to 0 because we can't have negative water. So then we just skip it if the total water above this p is ever less than 0. So our total stays at 0. Nothing happens. We reinitialize our values and we move our p over. So then we do our calculation again. Now when we go to our left, we see that 1 here is greater than our current max left. So then we update this value here to 1, but 0 is not greater than 1, so max left stays at 1. And then we go right. 2 is greater than 0, so then we update this max right value to 2. 1 is not greater than 2, we keep the 2. 0 is also not greater than 2, we keep the 2. 3 is greater than 2. And then we check the 1. 3 is larger. 0, 1, 2, all smaller than 3. 3 is still the max. Now that we have both of our maxes, we get the minimum between the two of them. So the min between 1 and 3 is 1. 1 minus our current height of 0 is 1. So we add that to our total, and total goes up by 1. Then we reinitialize our p as well as our initial values here. And now we just do this step for every single remaining value in the array. It's pretty tedious because, again, I'm just applying the same logic over and over again, but I think you get the idea of what we're trying to do. It's probably good at this point for you to do the rest of this array and do the same steps that I was repeating here, just so that you get an idea of what the logic and the rationale behind everything is. And then what I want you to do is I want you to try and take this idea and see if you can come up with a code for capturing what we've just come up with. I'm going to do it in the next lesson, but it's good to try yourself every time because you'll find that by trying it yourself, you get a deeper understanding of what we're trying to do with this solution. So if you don't get a chance to try it, that's perfectly fine. We'll go through it together in the next video.